Hi, as I already told, I'm Milos Meriak. I want to welcome you at the CCC Sputnik talk, which will hopefully give you an insight into the Sputnik hardware, the infrastructure, and hopefully will enable you. Test. Test. No. Test. Which will hopefully enable you to create your own hardware, the read from Sputnik, and to extend the extended protocols and create your own devices or use it as a remote control or whatever. I had, I think the best approach is to show you a quick insight into the hardware. Basically what is currently available in terms of documentation, what to find where, and give you a quick insight. If you have in-depth questions, we will have a Q&A afterwards, quarter hour. And you are all warmly welcome to join us at the Sputnik booth. We have several programming adapters there, and if you're interested in playing around, you can join us, and we will gladly show you how to extend the code, how to make your own modifications. Okay, I think now we are set. Okay. I'll give you a brief introduction into how this project emerged. We basically had a lot of thoughts about how to solve RFID tracking problems. We came to the conclusion that existing hardware is either astronomically expensive or simply unusable. So, for example, with common RFID passive tracking systems, the highest distances for tracking you can achieve are, say, 5 to 10 meters with passive tags, and you still have very expensive reader hardware. And anyway, it won't be possible to use passive tags for 2D locationing. So we looked around and searched for active tags, and we came to conclusions that they are simply not affordable for a large-scale installation like congresses and so on. So we decided to build our own hardware and make it as inexpensive as possible, to make it as open as possible by using mainly open source tools and publishing all the necessary information to make your modification. We had a field test. The first field test was half a year ago at the 23rd Chaos Communication Congress in Berlin. We basically set up 23 of the Ethernet-based readers we designed. The Ethernet-based readers are pretty simple. It's basically a single-chip Ethernet controller, 8-bit, and it's amazingly stupid, and it only forwards packets that it receives to a central server. The current Sputnik team consists of me and my wife Britta. Henrik is currently helping us with great effort, and he's working with us on the firmware to extend the OpenBeacon USB readers with better firmware. He's also worked with us for the last weeks really heavily. And Carsten Nohl joined us for implementing a meshing protocol. So the basic idea is, maybe you saw it already on our website, is we have a USB-based low-cost reader, which can be fully controlled with open source tools. And you can decide not to plug the device into a computer, but only power it with a battery or with a wall socket, and have it run autonomously. And the basic idea is to create a meshing protocol on this ARM-based USB node. So this is what we're currently doing, and as I said, you can join us at our booth, and all help is highly appreciated. Last year's visualization was done by Artcom. They did this, maybe some of you that saw it on the last Congress saw this cool 3D animation where you saw the avatars moving around depending on where you are, where the reader received you, and this was completely done by Artcom and many other people that wrote software for putting the data into the Artcom visualization system. You may ask why we did this. At first we looked at this 2.4 gigahertz stuff and it seemed like big voodoo stuff that you don't want to do in real life. But we said, so after reading plenty of books about high-speed analog design and HF design, we said the most simple solution simply to try such a design by yourself. If some of you want to try, already tried, they probably also found out that it's amazingly simple. It's if you find out what's important, then it's very simple to do 2.4 gigahertz design. It's nothing to be afraid. There are some rules. Some are only rules of thumb. Some are simple mathematical rules. And I think it's very simple that for example, some of you just take the parts they need from our designs and put them in their own designs. For example, for using it as a remote control or in autonomous robots and stuff like this. This is very doable, and even people with average layout experience can do this if they accept some rules they have to comply. So I say if someone wants to try it, just try and then fix the errors. It's much simpler as you think. Also, we didn't like that all RFID systems available on the market have a high lack on transparency. You buy a reader for an insane amount of money and you basically have to struggle to get low-level API information. Most cases you only get support for Windows systems. You have to reverse engineer the readers. So it's no fun at all. So therefore we designed before spending time and reverse engineering super expensive readers, the time is better spent for building our own reader. Also, we are obviously very interested in seeing how people react to this. Obviously there are lots of problems going on with RFID and tracking, and we want to evaluate if there is a good tracking possible, if it's possible to track people and for their own good, if you can have additional value from it. And at the end I will give you a short insight what rules we found out and how RFID tracking can be done in an acceptable way. And also, obviously, to supply all participants of a Congress and whatever with a tracking solution, it has to be pretty cheap. So we optimized it for price. And the outcome is that now you have a huge library of code where you just take the HF front end, which is really dirt cheap. You can have this 2.4 gigahertz front end added to own circuit board for say €2, something like that. So you can add this front end by taking our design examples and use our proven APIs to adapt it to every processor you want. I will give you a short introduction in this part too later. What is planned for the current convocation camp? Due to a lack of Ethernet-based readers, we made a fallback solution, and because we didn't want to cancel the tracking, we decided to take the few readers we actually have and put them only in shelters. So we will put 5 of the Ethernet readers in shelters. For example, here you see one of the readers, the black one, between the wireless access points. So we can only check in real time in which shelter persons are currently. We also will deploy 3 or 4 readers in the village areas. So there will be also have a non-continuous tracking of the most important parts. What we're currently working on, it's a pretty interesting project, is using this cheap USB nodes and use dry batteries. We have bought 72 dry batteries, so this allows us to deploy up to 35 battery-powered nodes, which will be spread all around the campsite, and these will gather the signals of the current tags. And the new tag design has some nice additional features. For example, you have a real push button there where you can rate locations. For example, if you press 1, you give a location a low rating, and you can press up to 5 times on the button, and then a high rating will be submitted. This battery-powered USB nodes will receive this rating and accumulate them over time. So the lifetime is yet to decide, but currently we think about 1 hour. So if you vote at a certain location, your vote will be stored there for 1 hour and will be averaged with all other votes in the last hour. So you can give a location a rating, and what Henrik mainly currently works on is to add a return channel where you can also see on your badge which rating the current location has. So the idea is that you walk around the campsite and you see the rating. So if you see blinking 5 times, you know, oh, there is something hot nearby, and you can try to find out what interesting event or whatever there currently is. So you have the feedback, you can vote, and you see the votes of other people's. And Carsten is currently working on create a meshing protocol between these rating nodes, so the data can be exchanged, and we will provide some things that will stream the data to the internet. So the idea is that we can create a non-real-time mood map of the Congress site. So the site is already there. It's not yet published officially, but it's basically derived from Google Maps, and the overlays are transparently created. The transparent overlays are created on our web server and will be overlaid over the campsite, so you can see, if we get the meshing running, a real-time mood map basically of the Congress area. Okay, we currently have 500 tags. They will be sold at the second day because we found out that we have a very bad problem. We used this neodymium magnets for attaching them to your t-shirt, and the glue turned out to be bad, so the magnets are falling off by themselves and you are in danger of losing your tag. So we're currently searching for a place where to buy 500 security pins so we can attach it securely to your t-shirt. So if someone knows where to get 500 security pins from, then help is greatly appreciated. This is the current tag. It's now circular. It's only 36 millimeters in diameter. You see the ceramic antenna, the push button in the middle, and basically the other design is the very same. We did one major change, that we used golden coating now, so the tags are not oxidizing that easily like the old ones. In the old ones, you probably have to use sandpaper to clean the battery contact to get your tag from the last Congress running again. Yeah, by the way, if you want to use your existing tag, you can come to our shelter at Art and Beauty, and we will reprogram it for you, so you can use your old tag from the last Congress if you brought them here. This is mainly interesting for people that are using the following schematics. You see where the individual parts are placed on the board. I now will show you the schematics. I came to the conclusion that usually people are really afraid of trying to read schematics because they look completely non-understandable. But if you want to change the code, or for example attach it to your robotas or whatever, or create sniffing devices or create keyloggers with Sputnik, you need to understand the schematics. Therefore, I will give you now a short introduction how to read schematics. It's basically very simple. You just have to believe in yourself. Hang on a second. Okay, the next slide. Sorry. The hardware consists again from a PIC16F684 microprocessor. We mainly chose this microprocessor because it's A, cheap, B, draws virtually no power, and C, you can buy it pre-programmed, and no other manufacturer, to my knowledge, provides such services. You can buy directly from microchips, so you don't have to pay annoying fees for distributors that are just reselling the devices. So it's on the end cheaper. But I personally also don't like PIC microcontrollers because they are not really high-level language capable. We again use this NRF24L01 2.4 gigahertz front end from Nordic Semiconductors. This is really, really great. You have to read the data sheet. It's readable, and it provides basically all kind of communication functions you need in hardware. So, for example, it provides acknowledging services. It provides a FIFO up to 3 packets. It decodes automatically MAC addresses. It checks CSCs. You can save insane amounts of power by just clocking in the data, turning your processor off, and the NRF chip will handle everything autonomously. You have to be aware that in most cases, the best solution to integrate in your existing design is not by using it with the PIC microcontroller and attaching it to your microcontroller, but by directly using the NRF24L01 HF front end. It's very easy to use. It has a SPI interface. To people that don't know SPI interface yet, it's, in my opinion, the most simple interface to get data into a digital device. You have a clock line, you can clock data in, and you get data out on a this front end. So you definitely have to think about the possibility of only using the NF processor, and we have a high-level API which is very easy to port to every setting and reading I/O ports, and everything else is done by the API. We again have this battery lithium-ion cell as a power supply. The push button is new, and we provide additional header for attaching piezo buzzers. So this is intentionally left blank. So if some people are interested of adding sound support to Sputnik tag, we will support them. In my opinion, this even people that are not don't have very much experience with embedded programming can do this task within 1 or 2 days. So this is, I think, a very simple way to pimp your Sputnik tag. Also, there is a second pin, so the program header is not wasted, where you can add additional I/O pin to your own custom hardware. These are the schematics. So the basic idea is that this is the top level sheet. On the top level sheet, you have these green boxes, and these green boxes indicate other sheets that are inside this. So if you want to get an overview, you look at the top sheet, and there you see basically you have 2 building blocks, a CPU and the RFB, it's a RF front end. And the only lines, the only lines that are used to communicate between those are shown here. So there are no other magic lines except of ground and power. These are global for all sheets. So basically, it's a very simple game. It's like in this fast food chains where you have this pictures where you have to follow a line. Here it is even more simpler. The lines are named. So if you have a line, I will zoom. Is this possible? Hang on a second. No. If you have a line, then the line is automatically connected if it shares the same name. So this makes a sheet more reasonable. So if you have a line here that's IRQ, it's automatically connected to another line that is also called IRQ if it's on the same sheet. This ensures that you don't have wild crossings between all kinds of lines and you lose completely track. So first look at the names for the lines and then you see where they go. This is the processor. I have a link for the data sheet. And then you know automatically, for example, you want to know how to toggle the clock pin. You follow the line for the clock pin. You see, okay, it's pin 10 and it's RC0. And then you look into the processor manual how to use this. But the normal use for you is, as I said, very simple. You just have to follow lines and look what is connected where. For example, if you want to turn off the or on the LED, you see here's the LED, and you have RC5. You just have to turn RC5 on, and then the LED lights. Or for example, here you have the programming connector, and here you see how the lines are individually connected. Oh, that's also an interesting part. There is also a new change in the tag design. You can choose between two operating modes. For the current use, you obviously want to constantly power the tag, but because it automatically sends data out. But if you move the 0 ohm resistors to this, there is a mode A1 and a mode B1. If you only connect this resistor, then you can turn on the tag with a push button. So for example, if you want to secure your door at home and you want, or your garage, you want to open it with a Sputnik tag, then this will be the most power saving possibility, because the tag then is only powered while pressing the button. That's the intention. So if you have application where you just want to have action while pressing the button, then you just move the resistor from here to here, remove this resistor, and you have a tag which only acts when pressed, and then the battery will easily last for years. And this is the RF front end. So if you do your own schematics, you just have to add this part and connect this I/O lines to your to free I/O pins. So that's basically all. And you just take the same values and have a look at our layout. And if you want, you can send us our layout and we will have a look on it if it's done in a proper way, or if you have mistakes, so you don't waste money on PCBs. So if you're interested, just send us your layout and we can check it. So the current functionality, every tag transmits now 6 to 8 times per second. This is very important because the area is very big. So we want to make sure that even if only every 20th packet is received, that you have tracking with 2 seconds resolution. Therefore, it's much higher than on the Congress, where the tag only transmitted every 1 to 2 seconds. Also, we changed the code that the blinking is not synchronous anymore with the transmitting because it would cost too much power. If we would blink 8 times per second, it only blinks 1 time per second roughly. So don't be confused. It really sends packets out 10 times a second. Then the pseudo-random generator is again seeded with a random seed. It again cycles through 4 power levels. So you can estimate the distance to a reader by checking at which power levels are received how often again. Yeah, and to make sure that if we have areas where the tag density is too high, we want to make sure that there we don't get a denial of service attack. Therefore, we have 2 channels. On one channel, you have a low frequency tag transmitting, and on the other channel, high frequency. So if we get too much sightings on a given area, then we just turn to the second channel where we have where we get much less beacons per second. Currently, it transmits on channel A 4 times as often as on channel B. Again, the transmission is encrypted by using XXTA block encryption and a 128-bit shared key. We use an incremental sequence number again to make sure that every packet is different, because if only 1 bit swaps in the packet, because of the block encryption, the whole packet changes completely. The shared key is protected by the usual CPU copy protection bits. This is an average security, so you can't take a simple program and read out the keys used. Again, the encrypted packets will be forwarded by our Ethernet readers in the shelters and sent to aggregator, where they will be stored after decryption. Yeah, and because of the encryption, the data gathering can be only done by the owner of the tracking system, which obviously knows the shared key. So sniffing, so it's I think a pretty good protection. How to write your own code for Sputnik? The entrance fee is pretty nice. Basically, you only need a PIC-Kit2 programmer. This is a pretty convenient device. You have yeah, it's USB. It has a USB interface, and so you can work on your laptop easily, and you can reprogram the devices easily with the Sputnik text with this programmer. We used the first for the current software using this high-tech PICC Lite compiler, but it turned out that only few people participated because you had to use the Lite version of the compiler, which only supports half of the flash. So we had to throw out the encryption for the Lite version, so everyone is able to build firmware images. So what we also will do in the next weeks is to port the firmware to SDCC. I personally hope that, because it's usually it's a very simple job to port this into a different compiler. This PIC 684 is perfectly supported in SDCC, and I hope someone will take a day and port it, but no one turned up and ported it, so we had to port it by ourselves. So if you're interested in porting it here on the Congress, we will support you as much as we can. You can sit at our booth, and so you have a direct connection to us, and we will assist you in porting it to SCCC, so more people can use the real compiler and reprogram the tags to their own use. This PICC compiler really sucks. You don't really want to work with it. Basically, you need average C compiler skills. I think the code is pretty readable, and you need obviously time. Porting, as already indicated, is pretty simple. You only have to replace some atomic functions and which deal with setting and reading pins. I think this is very, very simple to port it to a different processor. And if you have a bigger processor, then have a look at the OpenBeacon USB firmware, because there you have a layered API. And you definitely, if you want to work with either OpenBeacon USB or the CCC Sputnik, you have to read the NF datasheet, which is, for if you compare to other datasheets, pretty verbose. This is the new USB node I already indicated. You can either plug it to your computer and upload the sniffing software, so you can track people by yourself, or you write, for example, meshing. You use meshing code and other functionalities to create your own devices derived from it. Again, it doesn't need a computer. The computer is only needed for reprogramming, or if you want to gather the data for storage or whatever. But if you power it with a wall socket power supply, for example, like the ones I use to recharge telephones, these power supplies are available with USB socket. You can directly plug it into this wall socket power supply, and you have an autonomous node. It's a very, very convenient processor. It's well supported in Linux. You don't need special programming tools. You just plug it into a computer. You use free software to reprogram the processor, and it's not brickable. You can always revert to default USB code for uploading your firmware, so you can't destroy it only by smashing it to a wall. It provides also pretty much RAM and flash, so even average programmer, I think, can work in a good way with it. And to make it even more simple, we didn't dare to use, like with our OpenBCD project, where we had bad experience with implementing our own operating system, which basically, except of us, nobody can use. We now stuck to FreeRTOS, which is very good, documented in a very good way. You have multitasking, you have semaphores, you have everything you know from a desktop computer system programming. You have a emulated serial interface, and I think it's very simple to write code for this processor, even if you don't have an embedded coding experience yet. If you want to use it to extend your hardware, you have a RS-232 serial port. We implemented full DMA acceleration, so you can download the data from the NF at full speed. It doesn't block the CPU. Meanwhile, you can do different tasks. It easily can handle 2,000 packets a second, and it already has support for hardware acceleration for frequency hopping. These are the schematics. will go. It's basically very same, only a different CPU. It can be even reprogrammed under Windows. The GCC ARM toolchain is really great. It provides a very good assembler code from your high-level code. So I definitely suggest you using this GCC ARM toolchain. It's also available for Windows users, and obviously under Linux that's no problem at all. Yeah, and to make it even more simple for you, we now, like on the OpenBCD project, don't use anymore a USB debug cable, but we implemented a serial port emulation over USB. So you have a very convenient serial debug interface on a virtual COM port where you can change modifications and send debug output to your computer. And it's recognized out of the box in Linux, and in Windows you don't only have to supply an in file. No driver is needed to get it running in Linux, in Windows, and then you can use Hyperterminal or whatever to connect to the device. And as I said, multitasking is implemented. You can easily create a task if you're not sure how to write your code. It's really that simple. I want to show some user contributions. So far for the hardware part. Now I want to show you some user contributions. For example, Peter Merwald did a really, really great analysis of the tech data gathered on the last Congress For example, on this chart, you see which readers saw the same packet at the same time. For example, here you see that on floor C, the reader with this IP address and this IP address saw nearly 300,000 packets saw the same 300,000 packets than the other reader. And here you see, for example, that most packets are received on the same floor and few packets are even received 3 floors below. So Sputnik goes in some cases even to 2 concrete ceilings. This is a very nice front-end Andy Green created. We never made it public because it's very processing intensive. It takes around 1 second to compute such a picture, but then you see the sightings of the last 30 seconds for a given tag, and you can estimate the position of the user. For example, here you see that the user is obviously on this floor, but on the floor below, which was the hack center as far as I know, also a few packets were received. So I think here you can estimate that the user was somewhere here. And it's basically created by using image magic libraries for PHP. This is some prototype for estimating the position graphically. This was also Andy's idea that, for example, if you receive a packet here with only the smallest strength, then you know that a person is in this room. If you receive it here only with the highest strength, then you know the person is not near this reader. So we can cut away this circle from the low power circle. And same here, here's a kitchen. Here also only the highest packet, the highest power packets were received. So again, you can cut this away from the low power circle, and then you know that the person can be only here. Only what is missing is a clipping for the flat. So outside the flat, the person obviously can't be. This is some pictures of installation of last year. And these are the new Power Ethernet powered readers. You have one port where you can plug 802.3AF complying PoE Ethernet switch, and on the other side, or here you can see the bit R2 other switch where you can cascade multiple readers. Okay, in short summary, what experience we got and feedback from users. So basically, we came to the conclusion that monitoring is accepted if you users have immediate benefits, that they say, okay, if I wear this badge, then I can do this and this and this. I can know which talks I attended. I can probably see what other guys attended, the probably same talks. And so you have some kind of additional value. Otherwise, you won't wear it. So then the acceptance rate is much higher. And what's very important, which is the case for Sputnik tag, if you are fed up, you want not to be tracked, then there's a possibility you get your battery out and you know you can't be tracked in any case. And I think this is something that is missing in all current RFID tracking solutions, that you don't have some kind of user override where you can say, okay, now it's my private time, now I want to go to the loo or whatever, and I don't want to be tracked, or I want to get a cigarette break, I don't want to be tracked. So what's needed is a solution where you can turn off tracking. And obviously, you have to accept what happens with the data. Okay, here are some links. Basically, the OpenBeacon website. If you're interested in simple RFID, then it's openpcd.org. You can read MyFair cards, read and write to MyFair cards with this design. It's also based on the 89.1 SAM7 design, and Harald Welte implemented a very cool library set called librfid and libmrtd, which can be used to read out electronic travel documents by using our reader. This is the link to the NAF website and to the microcontroller. Okay, any questions? I hope you are not completely... Questions? Yeah, it's the shelter where you have this big sphere on top. Don't be distracted by the crews that are constantly building up lighting. We are in the backside of the art and beauty shelter, and we are really there. Believe it. So just come there. If you want to hack some code, we will help you. Any questions? I didn't understand the question.
Was it not possible to make a passive design that works without batteries?
A passive design?
Yeah, something that works without batteries, so that...
we came to the conclusion that a passive design is not doable if you want to track areas. A passive design is only doable if you, for example, track entrances and exits. But a passive design is not possible if you want to track spaces, because the field strength will be too high. You have to be below the allowed field strength. You have to implement a grid of passive readers, which have to be spaced, say, every 5 meters. And this is not realistic, to my opinion. It would be possible, but the effort doesn't make sense. For example, with this single reader, you can cover the whole room. Even in the last row, people are tracked with the single reader. And this reader is much cheaper than a passive reader. So therefore, we decided battery is acceptable, and we are working on that the battery lasts longer. For example, you can take out the battery and use the same battery for 10 congresses or whatever. Okay, any other questions?
You said that you were missing some pins. So where will you announce when we can buy?
I can't hear it. There is too much reverb.
Where would you announce so that we can see when we can buy?
I can't understand you. Can you come to the front? The reverb is too high. I only hear the reverb. Where you can... question was where to get the Sputnik tags, yeah? I think the best approach is that we just put out a poster on the art and beauty shelter from outside. So as soon as you see a poster on the outside of the art and beauty shelter, then the Sputniks are there. Currently there is no poster outside, but as soon as you see the poster, you know the Sputniks are available. But it won't be till tomorrow noon. So any other questions?
It's possible to use more than 2 channels?
I don't understand anything, sorry. Yeah, the question was if it's possible to use multiple channels. The chip itself supports up to 100 channels. 83 of them are legal in most countries. You can decide if you choose 2 megahertz bandwidth or if you choose 1 megahertz bandwidth. So with 2 megahertz bandwidth, you have 2 megabits of data rate, and you obviously have only the half amount of channels. So in 2 megahertz, you have 50 channels you can choose that are not non-overlapping, and at 1 megahertz, you can obviously choose 100 channels that are non-overlapping. And the chip supports to quickly jump from one channel to the other channel. As I said, Henry currently works on this multiple frequency firmware where you have a low traffic channel and a high traffic channel, and you can use then the code is already in Subversion, in a local Subversion system, but there you have a good example how to change it dynamically, the channel. And at least the OpenBeacon USB already supports heavy acceleration of frequency hopping, so you can easily multiply the aggregated bandwidth over air by hopping quickly. So you can have multiple, or say 20 or 30 readers that are talking to each other without interfering in terms of bandwidth. And the basic idea is that we have a hardware timer that is wired to a DMA start input. So you can pre-configure your NRF with the data to send, and as soon as the timer expires, the data is sent out at the very same time. So, and on the falling edge of the timer, you just reconfigure it. So you don't have any real-time problems, and you can implement a very high-speed, hardware-accelerated frequency hopping scheme, but only with OpenBeacon USB. In OpenBeacon Sputnik, you can, in CCC Sputnik, you can obviously also do frequency hopping, but not hardware-accelerated. Yeah. Another question? You have any more questions, you can just come to our booth and we will explain everything you want to know, and hopefully many of you will come because we obviously like if people are interested in our project, so we will tell you everything we know about it. Okay? So thanks for your attention and have a nice time on the Chaos Communication Camp.